Today, we are going to discuss how to determine band gap of a semiconductor by four probe method. Why the method is called four probe, we will discuss later. First, we need to understand what is meant by band gap. Here, specifically, we want to measure band gap of a semiconductor. I hope I need not to say about semiconductors. Uh, Semiconductor are those type of materials whose conductivity lies between that of metals and insulators. Here by conductivity, we mean the ability to conduct both heat and electricity. Now, when we talk about band gap of whatever material we consider, whether it is a conducting material, metals, semiconductor or insulator, we need to understand what is meant by conduction and valence band. Basically, whenever we are considering a single electron, then it has different energy levels. So if I consider a single electron, then it has several energy levels like this. On the other hand, whenever there is a cluster of electrons, that means a collection of electrons are present, and which is generally true in any type of material, then each electron contributes to its energy level. So, since there are a large number of electrons present nearby, within within that small region, the electrons which are present, their energy levels will be displayed like this. That means the energy levels of all the electrons are very closely spaced. That means their energy values are slightly different from each other. And when we have a large number of electrons, then this spacing will be so small, spacing between any two consecutive energy level will be so small that from outside what we will observe that it looks like a band. So band is actually meant by collection of a large number of energy levels. Now here we are talking about two specific type of band, valence band and conduction band. Now whenever a collection of electrons are there, that means there are a large number of bands are there. So we are drawing different bands here. See, these are different bands. So yeah, I am drawing here. Yeah, I am drawing 4 bands. Now, as per statistical mechanics, which we have discussed briefly when we tried to formulate the Planck's formula, then according to Maxwell-Boltzmann distribution, we know that we can estimate roughly the number of atoms or number of particles present in any energy level. And we have seen that the electrons or any type of particles always prefer to be in lowest possible energy levels. So in this universe, whatever type of particle you can think of, whether it is a charged or uncharged, heavy, massive or light and thin, whatever it is, the particle always try to be in lowest possible energy level. So in terms of bands, the electrons always prefer to be, or carriers, whatever type of carriers you can think of, always prefer to be in lowest possible energy band. Therefore, lower energy bands are generally filled. Lower energy bands are generally filled at low temperature, and higher energy bands are generally empty. Now, the topmost filled band is called valence band. The topmost filled band is called valence band. On the other hand, the lowermost empty band is called conduction band. So we'll take an analogy. Though it's not correct, still, for our understanding, let's consider a tall building. Say there are 20 floors in it. And if there is no lift attached to that building and the building is rent for sale, then what do you think, which type of floors, which type of flats will be rented first? That means the flats which are in the ground floor, or flats which are in the first floor, second floor, third floor, or any other floor. Which types of flats will be bought by people first? Remember, there is no lift attached. If you want to buy a flat from this building, which floor will you prefer?
Ground.
Ground or first or second, maximum third floor? Because we do not want to waste our energy in traveling through that floor, particular floor. We have to go through the stairs because there is no lift. So we need to supply our own energy to go there, and that we do not want. Therefore, lower floors, the flats in the lower floors will be occupied by people first, like this, and all the other floors will be unoccupied. So these floors are say occupied by people, and all these floors are not occupied. That is, they are empty floors. Now, we out of these four floors which are occupied by people, this one, ground, first, second, third floor, that is the topmost one. This is the highest floor. We call this one as valence. So this is our valence floor. So similarly, whenever we are talking about the energy bands, some energy bands are occupied by electrons. So suppose there are some these energy bands. Let me change the color. Say these energy bands are occupied by electrons. Now, out of all this, the topmost is this one. So we call this particular band as valence band. Now, we have so many floors unoccupied by people, but which one is the lowest floor? This one. This is the lowest floor, which is unoccupied by people. Though there are all other floors also, but this is the lowest one. We call it conduction. We call it as conduction. So here also we are observing all these bands are unoccupied by electron. But which is the lowest one? This one. We call this one as conduction band. We can think of it in this way. When the people are in that valence floor, that means in the third floor or any other floors below that valence one, a large number of people are staying there. So there is not enough place for people to roam around freely. People cannot roam around freely. They cannot, if they want, they cannot play a game there. Say some people want to play table tennis there. There's no space for that. Whereas from fifth floor onward, or not fourth floor, from the fourth floor onward, the flats are empty. So there is enough place to roam around. People can play the games there. So these are conduction. So conduction floor is that where people can roam freely. Whereas valence floor is that floor where people are bounded. People cannot roam freely. So we can think of another analogy. Say a highway consisting of different channels. Now in one channel, a large number of traffic is there. We have this one. We are observing that there are number of cars are moving, and it is crowded. So this is our valence one. Whereas this particular channel, you observe there is a very few cars are present. So that is, there is enough place for there, enough place for the cars to move there. That is conduction. But the problem is that if any car, suppose this one, wants to go from this valence channel to this conduction channel where it can travel freely, it can take up any speed it wants, but it cannot because of this barrier, because of the presence of this barrier. This is our band gap. So here, whenever we are talking about this type of model, like the roads we are discussing, or in the previous example we are talking about floors, then here this is the valence floor, the third floor was the valence floor, fourth floor was the conduction floor. In between these two floors, people cannot stay. People either have to stay in the third floor or they have to stay in fourth floor. You cannot expect people to stay on the stairs. It's not possible. So the region between third floor and fourth floor is forbidden for people to stay. The region between third floor and fourth floor is forbidden for the people to stay. That is the forbidden gap. So the distance between third floor and fourth floor is the energy gap, forbidden gap, band gap. Here also, this portion is the band gaps, which restricts the movement of any current from valence to go to conduction. Now, whenever we are talking about band, then we are talking about energies. It's not the distance we are talking about. Therefore, then the energy difference between conduction band and valence band is called forbidden energy gap or simply band gap. So, whenever you try to define band gap, please remember that it is not a distance. It is not a distance. Rather, it is the difference in energies. Difference between energy of conduction band and that of valence band. So, if suppose a valence band has an energy of 1.5 electron volt and conduction band has an energy of say 2.4 electron volt, then the gap between them is 0.9 electron volt. That is the unit of energy. It is not a distance. So it is the energy. So it is the separation between conduction band and valence band. That means in other words, suppose there is an electron here in the valence band. If you want to move it to the conduction band, that means if you want to energize it, if you want to energize this electron to conduction band, then you need to supply this amount of energy, which is, with this example, it is 0.9 electron volt. That is the amount of energy you need to supply. Then only the electron can be energized from valence to conduction band. Now, in conductors, or specifically in case of metals, there are a large number of free electrons. What is meant by that? We know about atoms, and according to Bohr theory, atom is composed of a nucleus of positive charge surrounded by 7 electrons rotating around the nucleus in different orbits. So suppose this is one electron. Now this electron is always rotating around the nucleus in specific orbit. So it is bound in this atom. It is not free. If this electron wants to go to any other portion, suppose this atom is a portion of a large crystal. There are other atoms there. There are so many other atoms are present. Now, if this electron wants to move around freely within this crystal, it cannot, because it is bound to stay within this atom. So this is a bound atom. Bound electron. This is a bound electron, and the energy of the bound electron is said to be valence band. So whenever we are talking about valence band, that means we are talking about some particles whose energy is in the valence band. That means those particles, those electrons, say, are not free to move. They are bound electrons because they are bound to roam around this nucleus in certain orbits. How can you make this electron free? So this electron is in the valence band. If you can supply at least the amount of energy that is required for the band gap, that means if you can supply this amount of energy, at least if you supply this amount of energy, you can supply more than that. If you can supply at least this amount of energy, then the valence electron can be made free. What does that mean? That means now you are supplying some amount of energy so that whatever bond is present in between the nucleus and the electron, you are breaking that bond. So in case of semiconductor, there is covalent bond. So you are supplying some amount of energy to break that covalent bond. When that covalent bond will be broken by supplying some amount of energy, then the electron is made free. Then the electron will be free. And when the electron is free, then we say the energy of the electron is in the conduction band. So in case of metal, we have a large number of free electrons. In case of metal, we have a large number of free electrons, even at a very low temperature. Low temperature means there is no very less amount of thermal agitation. You are not supplying heat energy. In that case also, there is a lot of free electrons. So we can understand that if we just think logically, it is possible that the separation, the energy separation, the energy difference between conduction and valence band for conductors must be very small. the energy difference between conduction band and valence band for metals or any conductor must be very small. It must be very small, so that by supplying a small amount of energy which can be supplied through thermal agitation, an electron present in valence band can be raised to conduction band easily. In fact, in case of metal, actually, if we can draw the band, suppose this is a conduction band and this is the valence band. In case of metal or any good conductor, actually, valence band and conduction band overlap with each other. And therefore, whatever electron is in the valence band, they are also present in conduction band. And that's why, in case of metal, there are plenty of electrons. There are plenty of free electrons, which are not bound to be present within a single atom. These electrons can roam around freely within the crystal. So this electron can roam around freely in any place if it wants. So this is the case of conductors. So you understand, in case of conductors, either the energy difference, that is the band gap between conduction band and valence band, very small, or conduction band and valence band just overlap with each other, so that a plenty of electrons are free. A good number of electrons are actually free. On the other hand, we have another type, insulator, where the valence band is almost or is completely filled by the electrons, just like this. Here you observe the channel. This channel is almost filled. Even in fact, at low temperature, the valence band of this type of material called insulator is completely filled. So here it is. You observe it's completely full, whereas conduction band is completely empty. That means there is no electron present in the conduction band. All the electrons are present in the valence band. That means all electrons are bounded. All are restricted within their respective atom. So if you want to make them free, you need to supply an energy which is at least equal to the band gap energy. That means this amount of energy at least you need to supply. But unfortunately, in case of insulators, this band gap energy is so large, that means the separation, energy separation between conduction band and valence band is so large that if you want to supply that amount of energy to excite and valence electron to conduction band, ultimately the material will be damaged. You are supplying a high amount of heat energy. You are supplying this amount of energy in the form of heat. Now the material cannot withstand that amount of heat energy generally, and it is damaged. So you cannot excite the electrons to the conduction band. That's the problem in the case of insulator, because energy band gap is so large. So this is the situation you can think of, that this channel, say valence channel, and so many cars are present that they cannot move. Complete traffic jams there. So as I was saying, here the band gap is relatively large. Now come to the semiconductor, and as the name suggests, its conductivity lies between that of conductor and insulator. That's why we cannot say we cannot say them as conductor, but it is semiconductors. Because at room temperature, it is observed that some electrons are present in the conduction band here. Some charges, some carriers are present in the conduction band. That means there are some charges missing in the valence band. Okay. That means if we say in terms of electron and holes, that means some electrons are present in conduction band and there are some absence of electrons called holes in the valence band. At room temperature. In fact, if you go to the absolute zero temperature, then the semiconductor behaves like an insulator, because at absolute zero temperature, the valence band is completely filled. No electron present in the conduction band. But the energy separation, the band gap, this band gap for semiconductor is relatively smaller with respect to insulators. That means whatever energy band gap was there for insulator, in case of semiconductor, that band gap is smaller, much smaller. As a result, when you place a semiconductor at room temperature, that means say 27 degrees centigrade, that means 300 Kelvin. So you are supplying some amount of heat energy, and that energy is sufficient to raise some valence electrons to conduction band. That means in in case of semiconductor, there are covalent bonds, and some of those covalent bonds will be broken, and some electrons, some charges will be free. That means they will be in the conduction band. Why is this possible? Because how we can break the covalent bond? Because the energy required to break the covalent bond is smaller. That means the energy difference between conduction band and valence band, what we call as band gap energy, is much smaller. And that's why we can supply that required energy in the form of heat energy or any other type of energy, so that the electron can be excited to conduction band, where it will be free. So this is the situation now. So this was the valence channel, whereas this is the conduction channel. Now we are taking a bypass. Through it, some cars can be now moved from valence to conduction channel, where it can speed up to the required value. So in case of semiconductor, as we have said, that the gap is smaller. So if we compare among the three types, metal, semiconductor, insulator, in case of metal, as we have discussed, the conduction band and valence band overlap with each other. This is the overlapping region. Whereas in case of insulator, the separation between conduction band and valence band, the energy separation, better to say, that is the band gap energy difference, is much larger. Whereas in case of insulator, there is an energy difference between conduction band and valence band, but that energy difference is much smaller in comparison to insulators. In case of direct band gap or indirect band gap semiconductor, what you can say that this is the energy or EK diagram, energy with K with propagation constant diagrams. That means energy is plotted along y-axis and propagation constant plotted along along x direction. In that case, you observe that it is not flat. The bands do not look like this. If they look like in this way, then we can say the separation between conduction band and valence band, energy difference between the conduction band and valence band is band gap. But in this situation, how do you define it? So you can say the band gap is the energy difference between the lowest point of conduction band and highest point of valence band. It is the energy difference between lowest point of conduction band and highest point of valence band. Or in other words, it is a minimum energy difference between conduction band and valence band. So that is the better way to define the band gap. Either we say that it is a energy difference between lowest point of conduction band and the highest point of valence band, or we can say it is a minimum energy difference between the conduction band and valence band. Now we'll come to the basic thing. How will we try to measure the band gap of a semiconductor? We cannot directly measure band gap. We can measure the band gap of a semiconductor with the help of measuring the resistivity of a semiconductor. And resistivity of a semiconductor can be expressed by this formula. Remember, in case of metals, you have used the formula for resistivity. Whenever you have measured resistance R equals to rho L by A, remember? That was for metals. But here we are talking about semiconductor, because the aim of the experiment is to measure the band gap of a semiconductor. So basically, we will use the germanium semiconductor. So how will you measure that? And for that, the formula is this. Rho, that is resistivity, equals to V by I. V is the voltage, I is the current. Now, what is this 2 pi s and G7? First, understand this is our semiconductor. This is the semiconductor whose band gap needs to be measured. Now, for that, as the formula suggests, we need to measure voltage and we need to supply some current. Now, whenever you need to supply current to the semiconductor, for that we require two channels. We require two probes. So we are using these two probes for the current movement. through the first probe, current enters to the semiconductor, and through the fourth probe, current leaves the semiconductor. So we require 2 probes for current, and amount of current can be measured with the help of a ammeter or millimeter, whatever required. Next thing you require to measure the voltage. Voltage is the potential difference between 2 points. Therefore, we require again 2 probes. So these are the inner 2, say 2 and 3. These 2 probes. These 2 probes are used to measure the potential difference, the voltage in this semiconductor. And that's why to measure this voltage and current, you require 4 probes. That's why the method is called 4 probe method. You require these 4 probes to measure the voltage as well as current. Now, you are using these 4 probes, and we are assuming that these 4 probes are connected in such a way that the separation between any 2 consecutive probes is constant. So if you observe this one, this distance between 2 consecutive probes is constant, and we are saying that is S. That one is your S. S is the distance between 2 consecutive probes. So this one, or this one, or this one. This is your S. Now, in general, this is the formula for resistivity. V rho equals to V by I into 2 pi S is the resistivity of a semiconductor of infinite width. That means when we assume the width is of infinite. That means for that particular case, the theoretical value of rho will be V by I into 2 pi S. If we assume that the semiconductor is of infinite width, but practically there must be a width of a semiconductor. Like here, this is the width of the semiconductor, W. Therefore, we need to give some, so that means if I use this formula, V by I into 2 pi S, for a practical semiconductor having a finite width of W, then it will give some error. To rectify that error, to remove that error, we are using a correction factor, which is G7 correction factor. There are actually different types of correction factor depending on the shape, size of the material you are using, and whatever material you are using below the semiconductor. Like here, we are using a conducting sheet below the semiconductor. So we have different types of correction factors for that. The semiconductor we are using and how it is placed within the instrument, we are using a correction factor called G7 correction factor, which depends on 2 quantities: the separation between 2 consecutive probes, that is S, and of course the width of the slab, width of the semiconductor slab. So it is 2S by W log 2, ln2, natural logarithmic of 2. Now, as for our setup, the instruments, the apparatus are fixed. So this 4 probe setup is fixed. That means the separation between 2 consecutive probes will be fixed, and we are using a same material throughout the experiment. So what I was saying is that since throughout this experiment the apparatus remains same, and in doing that, the spacing between 2 consecutive probes remains same, and we are not changing the material because we need to measure, we need to determine the band gap of that semiconductor. So semiconductor remains fixed, so width of the semiconductor remains fixed. So these 2 are predefined to us, and we know those values. Therefore, we know G7. So if we put those values in the formula of G7, the simplified formula for G7, then we get the value as 5.545. Okay, so this portion is constant. So 2 pi S G7, this portion is actually constant for us. Throughout the experiment, what we'll do, whatever current will supply to the semiconductor, whatever amount of current we supply to the semiconductor, that will remain fixed. So we'll treat I as constant also. That means the whole quantity, this whole quantity is actually constant. That means when we start the experiment, we know the value of this constant, because I will be fixed throughout the experiment. 2 pi S by G7 is always fixed. So we know the value. So this is constant. So only variable quantity that could be is V. Actually, the voltage depends on the temperature of the material. So if we can change the temperature, then voltage will be changed. Therefore, we can say, in other words, the resistivity depends on the temperature, and the temperature dependent form of resistivity can be expressed by this: rho equals to rho naught e to the power Eg by 2kt, while Eg is the band gap that we need to estimate. We need to measure this band gap. This is our ultimate aim. K is Boltzmann constant. You have used it so many times in quantum mechanics. T is the temperature in absolute scale. That means if we are using the room temperature, say 27 degrees centigrade, we can write it in 300 Kelvin. That will be our capital T. Rho naught is a constant which depends on the material. So if we try to plot this resistivity with temperature, it will look like this. So you observe resistivity decreases exponentially with temperature. If we increase temperature, then resistivity decreases for semiconductor, and it should, because think of a semiconductor. Now if you, and there are some free, suppose it is a okay, first I am considering this is a only group 4 element. That means pure semiconductor I am thinking of. So in that case there is a particular number of electrons, free electrons, and there is a same number of free holes present in that semiconductor. Now, if you can increase the temperature, then what happens? If you increase the temperature, then more and more covalent bonds will be broken. If you increase the temperature, that means you are supplying the required amount of energy to break those covalent bonds. And then some bonds will be broken. That means more electron hole pairs will be created. That means conductivity will increase, because you are increasing more free carriers. You are increasing more free carriers. Free carriers are increased. That means conductivity will be increased. In other words, resistivity, which is inverse of conductivity, will be decreased. So that's what happens here. With increasing temperature, resistivity decreases continuously. Now we need to measure the band gap, Eg. So what we require, first thing, we require a lot of values of rho for different values of temperature. That can be done, because if I increase the temperature, if I change the temperature, V will be changed, and when V will be changed, rho will be changed. So we can have different values of rho for different values of temperature. That can be estimated from the equation that we have observed, from this equation. If temperature is changed, then V will be changed only. V is the variable here only. V will be changed, as a result, rho will be changed. Okay. But if I have the table, suppose I have the table of temperature, some temperature values I know some rho values, so that I can plot this type of graph. Then also, how can I estimate Eg easily? It's very tough to estimate it. What we'll do, rather, we'll take log on both sides. We take natural log on both sides. We take natural log on both sides. You observe, so left hand side will be log rho, right hand side will be log of rho naught plus log of e to the power Eg by 2kt, that is Eg by 2kt only. Log of this quantity gives you only Eg by 2kt. Now what we can do, instead of plotting temperature along x-axis like this, instead of plotting temperature along x-axis, we will plot 1 by temperature, that is inverse of temperature along x-axis. So along x-axis, we are plotting inverse of temperature. Along y-axis, instead of plotting resistivity, we will plot log y. Okay. So you understand, then this whole thing, if I say this whole thing is m, and this whole thing, if I say as c, then it will look like y equal to mx plus, where x is temperature inverse, y is log rho, c is log of rho naught, which is another constant, and m, the m is Eg by 2k. M is Eg by 2k, and this is an equation for straight line. This is an equation for straight line, where m is the slope of the line and c is the intercept. So if I can plot it, if I try to plot now 1 by t along x-axis, log rho along y-axis, then it will look like this. You observe, this is the plot now. Log rho along y-axis and t inverse along x-axis. So that its unit will be Kelvin inverse now. Within a certain range, you observe within this range, up to this range, within this range, we are observing this straight line nature, y equal to mx plus c, where y equal to mx plus c is the straight line. So this portion we are observing. So the semiconductor nature of the material is observed through this region. The semiconductor nature is observed through this region only, where m is the slope and c is the intercept. So we do not bother about intercept. We do not require intercept. That's why we can shift the x-axis. We can shift the y-axis. Here, instead of 0, 0, we can shift the x or y, because we are not interested in a curve passing through origin. This is not a curve passing through origin. Therefore, within this region, this is our straight line, and within this region, we can find out the slope. But what about this region? What about this region? You observe this region doesn't show the straight line nature. That means semiconducting nature is not displayed here. Now, what is this region? You observe temperature inverse is increased along x direction. Temperature increased. So temperature inverse is increased. So this is the direction along which 1 by T increases. That means this is the direction along which temperature decreases. So what is the direction along which temperature increases? This is the direction, negative of x-axis. So this is the direction along which temperature increases. That means this point is this point corresponds to the lowest possible temperature which we have measured. Suppose we have started from 30 degrees centigrade. So this corresponds to 30 plus 273 Kelvin. So this is the lowest temperature, and with temperature is increased along this direction, so that temperature inverse actually increases along positive x direction. So this region is actually the low temperature region, low with respect to the other portion. So within this region, the semiconducting nature has not been shown yet. The material hasn't shown its semiconducting nature yet. That's why we are not observing that straight line portion. So when we are very sure that the material is now showing its semiconducting nature, then only we can start measuring. And that happens for your data when the temperature is above 60 degrees centigrade. Then the material truly showing its semiconducting nature. And within that nature, that means that's why within this range, that means if I say this temperature corresponds to 60 degree and this point corresponds to 140 degree, then in the centigrade, then within this range we can find out the slope. But how will you find out the slope? Now for the other experiments, suppose in case of Hall or Young's, you had, sir will discuss it in more detail, you had this type of graph where the line was passing through origin, and that's why you could take any point, any arbitrary point, and for that arbitrary point you have estimated y as well as x, then slope was y by x. The slope was only y by x, but it is not passing through origin. So what we can do, within this straight line region, we'll draw a triangle like this. We'll draw a triangle, and the slope can be determined from this triangle. The slope will be delta of log rho, that is this length, by delta of the perpendicular by base of that small triangle or large triangle you draw. That will be the measurement of slope. So if we can draw the log rho versus temperature inverse curve, then within the straight line portion we can find out the slope. Once we know the slope, then from this formula Eg equal to 2k into slope, we can estimate the band gap of the semiconductor. Because K, Boltzmann constant, is known. Only you need to find out the slope. If we know the slope, we can multiply with 2k and find out the band gap. If you use regression line and a regression analysis, then you can directly estimate the slope from the regression line. You can use that value of slope to calculate the band gap of a semiconductor. But remember once again that this graph is not passing through origin. It has some intercept. Be careful. These are the apparatus we require. So we can have two types of systems. Either we have a system like this, which includes all the things at the same place. Like what you require, you need to supply some current. Then that means either you can take a current supply, a current source, or you can use this 4-probe setup, which can supply the amount of current you require. So if you just connect this probe, this knob towards the current region, the current portion, then the required amount of current, suppose it is asked to supply 4 milliampere current, then you can adjust 4 milliampere and supply that amount. How will you notice? When the knob is towards current, then this milliampere will be displayed. We will observe it, and with that, this is the display. Similarly, when you try to measure the voltage in millivolt, then you need to move the knob towards voltage side, and the voltage will be displayed here, and this millivolt LED will be activated there. There is an oven here, which can also be activated through this oven knob. What is the purpose of the oven? We need to supply that heat, because we need to change the temperature of the semiconductor. That's why we are using this oven. The whole setup, that is the material within the stand and the 4-probe arrangement, will be placed within this oven. When the oven is activated, it will automatically increase the temperature. At certain intervals, we will measure the temperature. How we can measure the temperature? Either we can use a thermometer, or we can use a digital meter also, like in this setup. So here again, this is the oven in which the probe arrangement with the sample is placed. As I was saying, that we can supply the current to a current source. So this is the current source, which also measures the amount of current. Like here we are observing that it is showing 3.03 milliampere. The voltage can be measured with a separate voltmeter like this one. Temperature can be measured with a thermometer or through a PID controlled oven, which also shows the temperature with the 0.1 degree centigrade accuracy. That is, this count of the instrument is 0.1 degree centigrade. So these are the apparatus we can use. With the help of this apparatus, what we need to do, we need to supply the amount of heat so that temperature of the sample will be increased. So we'll need to change the temperature at certain intervals. Say initially we will change the temperature at an interval of 5 degrees centigrade. Then when it will be in the semiconductor range, that means we'll get the straight line portion, then 10 degree interval will be sufficient. And at those intervals, what we need to do, we need to only observe and record the voltage at different temperatures. That's all. So first, we will observe the demonstration.
Good afternoon, students. Now you can see the total 4-probe setup with oven, thermometer, and 4-probe setup. So this is the 4-probe setup. This is the thermometer. Yellow color stick is this is the thermometer, and this is the oven within which the total 4-probe and semiconductor is placed. Now you can see there are 4 probes, and exactly below the 4 probes we can find out the semiconductor is placed in rectangular shape, and the mercury bulb of the thermometer is very close to the semiconductor. By this you can measure the temperature of the semiconductor, and total setup is inserted within an oven. And this oven is connected with the 4-probe setup. The power supply is actually power is supplied from the 4-probe setup to the oven. Now I switch on this oven. I switch on this 4-probe setup, and you can see there is a digital meter. Now the digital meter is showing the current which is passing through the semiconductor through the 2 external probes, and the unit is of milliampere. And there is a knob by which you can change the same digital meter to milliammeter to voltmeter. So now the knob towards the current side, that's why you are observing the currents in the digital meter with milliampere unit. If I turn this knob towards the voltage side, the same digital meter showing the voltage within the semiconductor, voltage drop within the semiconductor with millivolt unit. So first of all, you have to set a constant current through the semiconductor by this knob. You can vary the current to the semiconductor by this knob. So if I set it in very close to 4, so this is the 4 milliampere current is already passing through the semiconductor. And now I turn this knob towards the voltage side. Now you can see the voltage drop in the semiconductor for room temperature. Actually, now the oven is in switched off condition. So the temperature within the oven is now of room temperature. And you can measure the temperature by the thermometer. There is a mercury column from which you can find out the exact temperature within the oven. So this is the room temperature and the corresponding voltage drop within the semiconductor is this one. The reading is showing 51.4 millivolt, but there is a knob. This knob is in the left hand side. There is a into one. So if I place this knob towards the into one side, there is the error symbol is showing in the little meter. And if I turn this knob into 10 side, then you can see a particular voltage reading in the little meter. Actually, if I turn this now towards the into one side, this reading is outside the range of the voltmeter. That's why there is the error symbol. And to make it within the range of the voltmeter, I have to turn this now towards the into 10 range. Actually, when you are noting down the voltage reading, you have to multiply 10 with the reading. So now, if you show the reading is 51.5, so you have to note down the voltage reading 500 14 or 550. Okay, so this is your reading for voltage. Now I turn on this oven. This is the switch for oven. If I turn on this oven, there is a LED, another LED is glowing now. This is connected with the oven. So actually now the current is supplied to the oven, and you can see the temperature is gradually growing up within the oven, and the temperature you can measure from the outside of the oven from the mercury thermometer, and corresponding voltage is going downwards. So if you increase the temperature, the voltage, first of all, voltage is going downwards, and for each and every temperature, you have to note down the voltage from this voltmeter. So first of all, you have to start from the room temperature. It is already noted, that is the room temperature and corresponding voltage. After switch it on, the next temperature will be 35. So when the mercury column raised to the 35 degrees Celsius, just note down the voltage from the voltmeter. And this process is continuously running. So then when the next temperature comes to the 40 degrees Celsius, then again note down the voltage. When it comes to the 45, again note down the voltage. So you have to continue up to 140 degrees Celsius. First of all, the interval will be of 5 degrees Celsius, and after 65, it is the interval of 10 degrees. So you have to continue up to 140 degrees Celsius, and for each and every case, you have to note down the voltage. So this is the process.
Right. So this is the kind of data table that would be supplied to you. The data table will be filled with the first, two columns, that is temperature and voltage, that will be given to you. So this is a sample copy. Let us say you will have different results. You will have different readings. So this is just to show you how you are going to complete the table and then draw the graph. So let us say the constant current flowing through the semiconductor is 6 milliampere, say for example. So in your data sheet, it might be different. In this case, the current that is flowing through the semiconductor is fixed throughout. So V by I, the formula that was there, V by I into 2 pi S divided by G7. Apart from V, everything is constant. Let me go back to the formula a bit so that you can understand. So this. So please check. This is the formula. This is the formula where 2 pi S is a constant because S is fixed. G7 is the correction factor, that is also constant. The current flowing through the semiconductor is also constant. So all of this is a constant which you can calculate and keep it in your calculator as to So this is a constant. All you need to do to find out the resistivity is you have to plug in the values of different voltages. And as BG sir was mentioning, you know that for a semiconductor, if you increase the temperature, the resistivity will decrease. And with that variation, we will have a graph. That is, the graph will be between this resistivity and temperature. And from the slope of the graph, we will calculate the band gap. So we know in physics that for a semiconductor, if you increase the temperature, the resistivity will decrease. Now, this is the formula that you will use to calculate the resistivity, where 2 pi s, G7 and I, they are constants. So if temperature increases, and if the resistivity has to decrease, then you will note that the voltage will also decrease because the resistivity is directly proportional to the voltage. So if you increase the temperature, the voltage across the semiconductor probe will decrease, because in only in that case the resistivity will also decrease, which should be the case. So if you look at the table again, let's look at the table again. So this is your G7 fixed, current I is fixed, and this is S. So you can see the temperature is increasing. So from by 5 degree we are increasing the temperature initially, and then after 70 we are increasing it by 10 degrees interval. And you can see the voltage that will be supplied to you. You can see that the voltage is decreasing as you are increasing the temperature, which means that the uh, resistivity will also decrease. So the first thing that you need to do is you need to convert the degree Celsius temperature into the usual scale, that is the Kelvin scale for working. So you will add 273 to all of your readings. So this will be your first thing. So add 273 to all the temperatures and you will get this column filled up. Next, remember you have to plot the graph between temperature inverse and ln rho, that is natural log of rho. So your temperature inverse should be along x-axis. Now you have the temperature in Kelvin. You take the inverse and you can fill up this column in Kelvin inverse. Next, you will calculate rho using that formula V by I into 2 pi s divided by G7, where I, G7 and 2 pi s, they are all constant. You just put in the value. So for temperature 30 degrees Celsius, you will just put in this value 621 millivolt, and I is 6 milliampere, 2 pi s and G7. You will calculate rho, and if you calculate rho, then you will calculate ln rho. Please keep in mind, I'll come back to this. This is ohm centimeter, the unit. This is ohm centimeter, the unit. So you will not change the unit of S. Do not change the unit of S to meter. Keep it in centimeter as it is. G7 is a constant. So now if you have rho, you will have ln rho. So this is the kind of table that you would see. The temperature, you convert 30 to add 273, you will have 303, and this is your temperature in temperature column in Kelvin. Now, if you inverse it, you will have this. Do not get confused with this E. This is nothing but 10 to the power of minus 3. So, if you inverse 303, that is 1 divided by 303, you will get 3.3 into 10 to the power of minus 3. And my suggestion is, it is our suggestion that you keep your reading in terms of 10 to the power of minus 3. Because in your calculator, the moment you put in your calculator 1 divided by 303, let us say this inverse, the calculator might show you something like this, 0.0033, something like this. It will show you, right? So what I want is, I do not write it in this fashion. Write it 3.3 into 10 to the power of minus 3. Okay. Similarly, your calculator for 308, 1 divided by 308 will show you 0.00324. So do not write it as 0.00324. Instead, write it as 3.24 into 10 247 into 10 to the power of minus 3. So keep it in terms of 10 to the power of minus 3, because when we will plot, we will see that it will be easier for you to plot it. So keep everything in your T inverse as 10 to the power of minus 3 multiplied by 10 to the power of minus 3. So now you calculate rho from that formula, and please make sure that here there is a millivolt. So remember the formula. The formula was V by I into 2 pi s G7. S would be kept in centimeter, which is already there, and G7 is a constant. So if you want it in ohm, then V should be in volt and I should be in ampere. But you see that V is in millivolt and I is also in milliampere. So no need to worry. Even if it is millivolt, and even if it is milliampere, the millis would get cancelled out and you will have volt by ampere, which is ohm. So if anything is given in volt or if anything is given in ampere, convert it into units, into proper units, so that you get V by I as ohm. So probably maybe in your table you check it yourself that you should have these two units in correspondence, so that you can have ohm. If this is in volt, then this should be in ampere, or if this is in ampere, this should be in volt, or if this is in millivolt,
Actually,
this should
TRC,
also.
sir,
Hmm.
in their given data, the voltage is given in volt unit. So they have
Okay, okay.
it will be
So
better
convert
if they
better if you
convert the
convert
current.
current. So what sir was mentioning, that if you look at your table, in your table there is a change. Instead of millivolt, in your table we have supplied it the voltage in terms of volt. Volt. The unit is volt rather than millivolt, and the current is in milliampere. So our suggestion is you convert current to ampere, because you have to convert it once. But if you convert volt to millivolt, you'll have to convert it for 16 readings. So keep all of this in volts and convert current to ampere, milliampere to ampere, so that you get it in terms of ohm centimeter. I repeat, keep S in centimeters. So again, take the natural log. Please do not take log 10 base. ln is natural log. So in your calculator, there are two logs. One is log to the base 10 and one is log to the base e, which is the natural log, ln. So take the natural log of this row and you will have this thing. So next thing that you need to do is you need to plot ln row along the y-axis and t inverse along the x-axis. So your next job is to plot. So if you plot ln row along the y-axis, this is your ln row and this is your t inverse. Now you see that I was telling you that keep your answers in 2.24, 2.4 into 10 to the power of minus 3, 2.5 into 10 to the power of minus 3. You see that you have written only this. But you should keep in mind that everything is multiplied by 10 to the power of minus 3. You write it just once. You write it just once. And it will be implied that it is multiplied, this 10 to the power of minus 3 factor is multiplied with every reading. Do not think that they are 2.4, 2.5, 2.6. It is basically 2.4 into 10 to the power of minus 3, T inverse. This point is 2.5 into 10 to the power of minus 3. But if you write every time, if you write 10 to the power of minus 3, your x-axis would get clumsier. So to avoid that clumsiness, you write only 2.4, 2.5, 2.6 and like that, and multiply that 10 to the power of 3 to all of them. So it will be implied that 10 to the power of minus 3 is multiplied to all of the readings. Is it okay, everyone?
Yes, sir.
Right. So you will get this kind of a graph, and as DG sir was mentioning, you can see there is a portion which is straight line, but after which you can see a curve. You can see a curve. So it is preferable that you draw the straight line after 60 degrees Celsius. So as I was mentioning, from 60 degrees centigrade onwards, that is this below, not before that. Below this, it is basically you will find a straight line. So if you look at 60 degrees Celsius, what is T inverse? T inverse is around, for 60 degrees Celsius, T inverse is around 3 into 10 to the power of minus 3. So try to draw the straight line from 3 into 10 to the power of minus 3 and 2.421 into 10 to the power of minus 3. So try to draw a straight line between these points, all these points. These points will lie more or less in a curve, not a straight line. So try to draw the fitted straight line between these points. That is starting from 2.4, that is the lowest value of T inverse, which implies the highest value of T, that is temperature, till 60 degrees Celsius, which implies 3 into 10 to the power of minus 3. So your straight line should contain these points. So if you draw a straight line, more or less, you can see the straight line is more or less this. So just extending beyond 3, you can see. This is the starting point, 2.4. 2.4, this is the highest temperature. Please understand, T inverse is increasing in this direction. That means temperature is increasing in this direction. If T inverse is increasing in this direction, temperature is increasing in this direction. And you can see that as temperature is increasing in this direction, ln rho, that is the resistivity, is decreasing along with increase of temperature, if you follow the line. So when temperature is increasing from right to left, the resistivity is also decreasing, as it was expected for a semiconductor. So more or less around 3, you can see this is 3 into 10 to the power of minus 3. So this is the point of 60 degrees Celsius. So if you take this point, try to draw a line, straight line from this point onwards, right up to the starting point. Other than this point, the points above these will form a kind of curve. So if you also draw a freehand curve, so try to draw a freehand curve joining the points, the curve would look like this. But the straight line should be from 3 into 10 to the power of minus 3 to this. So this would be a straight line. Whatever way you choose to draw, either you can choose to draw it in the best fit way, the regression line, or you can draw it using your eye estimation. So once the straight line is drawn, remember DG sir was talking that it is only behaving as a semiconductor in this straight or linear region. For this graph, only in the linear region, it is behaving as a semiconductor. So if you want to find out the band gap, you have to take the slope for this linear portion of the graph. So next thing what you need to do is you need to draw a triangle with on this linear portion. See, the triangle is drawn from here, see, around 3. It is not being taken above this, above 3. See, the triangle is not being taken above this, and this lower part is within this. So this triangle is drawn within the linear part of the graph. So if I take this triangle, then what is the slope? So this part, this length, I can easily calculate this length from my graph. That will be delta ln rho. And in my case, it is 1.94. So this length is delta ln rho. And for this triangle, the base distance or the base length is my delta T inverse, that is the x-axis. It is 0.48. You can see it from here. This is slightly above 2.5 and this is around 3. So you can see if you subtract these 2 points, the value would be around 0.48. But remember, everything is multiplied by a 10 to the power of minus 3. So you do not forget to do this. This is the most important part. It is not just 3 minus 2.52. It is not just 3 minus 2.52. It is 3 into 10 to the power of 3 minus 2.52 into 10 to the power of 3 minus 3. So the answer is 0.48 into 10 to the power of minus 3. So this is the base length and this is the height. So you know the slope. The slope is, so from the slope from the graph is delta ln rho by delta t inverse. And delta ln rho is 1.94 and delta t inverse from my graph is 0.48 into 10 to the power of minus 3, which comes out to be this. And please, this won't be Kelvin inverse, this would be Kelvin. There is a mistake, this would be Kelvin. Okay, so this is your slope from the graph. Is it okay till now?
Yes, sir.
Right. So if I have the slope, the Boltzmann constant is given in terms of electron volt. See, the Boltzmann constant can be written in terms of joules per Kelvin, and it can also be written in terms of electron volts per Kelvin. If we write the Boltzmann constant in electron volts per Kelvin, our band gap will also come in terms of electron volt. So Boltzmann constant is supplied to you, the value. What is the band gap? The band gap is 2 into Boltzmann constant into slope. So Boltzmann constant is here, slope is here. You just multiply them and you get in terms of electron volt as 0.69516. So up to 5 decimal digits that you are getting in electron volt. So this is your band gap that your calculator might give you. So this would be the range. Around this you will get the value. So by looking at the band gap, you can understand this is a germanium material. Germanium has a band gap of around 0.7 electron volt. So this is the band gap of this material. Now, should you write all the 5 decimal digits? That will be decided by the error calculation formula. So let us look at the error calculation formula. So the band gap was measured and this is the error calculation formula, the proportional error. So delta Eg by Eg is equal to delta of delta ln rho by delta ln rho and del of delta T inverse by delta T inverse. Let us understand the meaning of each one. You already know what is delta ln rho. If I draw the graph again, please understand, then this was your graph, the straight line part. And if I draw the slope, if I draw the triangle, this was your delta ln rho. And this was your delta T inverse. And you know it already from the graph. So this you know the height of the triangle, and this you know the base of the triangle. What about this one? This, the numerator one, this is the smallest division along y-axis. ln rho is plotted along y-axis. So whatever scale that you take, it will depend on that. So this is the smallest division along y-axis and this is the smallest division along x-axis. So let us say if along your y-axis you have taken 30 divisions as 0.5, that is ln rho is 0.5, is incremented by 0.5 along 30 divisions. So what is one smallest division? One smallest division will be 0.5 divided by 30. Similarly, for the x-axis, let us say for 20 divisions along x-axis, the increment in delta T inverse is 0.5 into 10 to the power of minus 3. So what is one smallest division? One smallest division is 0.5 divided by 20 into 10 to the power of minus 3. And this, you remember, is the value of the height of the triangle, and this is the base of the triangle. So you put everything in there, and the proportional error that you get is 0.06067. So that is the proportional error. For truncating your result, you need absolute error. So you remember Eg, your calculator gives this value. So for absolute error of delta Eg, so you know this, So the absolute error delta EG is always equal to the proportional error, that is delta EG by EG into EG. So you will have to multiply the proportional error and the EG value to get delta EG, that is absolute error. So absolute error is, you can see the proportional error is here, the proportional error is here, and this is the EG value. So what do you get? You get 0.0421 electron volt. That is the absolute error in the calculation of EG. Next thing, what do you need to do? You know this very well, that you'll have to write your result in this form, that is EG plus minus delta EG. So your EG is this and your delta EG is this. So if you add and subtract these two, then 6 will not be changed because you are adding and subtracting 0 from 6. So I am writing down over here 0.0421. So if I'm adding and subtracting this delta EG from EG, 6 will not change. 9 would change, because if I add 4 to 9, 9 would change, or if I subtract 4 from 9, 9 would change. So 9 is a variable thing. I am not sure about 9. So if I'm not sure about 9, I cannot write it afterwards. So I'll have to truncate with 9. I cannot write after this. And even for 9, I am not sure. I'm sure about 6. Is it okay? So what do you get? So this is EG according to your calculator. The absolute error is this. So the estimated band gap is 0.6 with a 9 bar plus minus. You even truncate this up to 2 decimal digits because this is where it is affecting. So this is your estimated band gap of the semiconductor.